by parts, so that you should be able to do, is equal to minus 2 cosine of x plus an arbitrary constant, let's call c1. Because remember, the derivative of cosine is minus sine, right? Okay, so all we have to do is that integral over there. Okay. So I need the integral of y e to the minus y dy. Okay, you know the old integration. I know usually people with UDV, I'm going to say let u equal y, and the differential of v, I'll be e to the minus y dy. So we use the formula, the integral of u dv is uv minus u du. Okay, and the reason I chose u equal to y, because then I can do the integration that's left, right? If you chose them the other way, then you'd be worse than you started. So u equal y dv equal this. So it's clear, therefore, that du is just the differential of y, right? And v is easy, it's minus e to the minus y. Okay? So using integration by parts, and again, if you don't remember this, you must review it on your own. Integral of y e to the minus y dy, it's going to be u times v, so it's minus y e to the minus y, right? V, y, e to the minus v, okay, so that becomes minus y e to the minus y. This becomes minus e to the minus 4, right? So be careful, all those minuses in there, right? Hope I didn't make a mistake, okay? Which basically says that the integral of y e to the minus y dy, let me pull out a negative e to the negative y, and they're going to have 1 plus y, right? Well, negative e to the negative y. Okay, so let's go to the left-hand side. So we have e to the y, right? And now I need the integral of y e to the minus y with the negative sign. Okay, it becomes plus e to the minus y, parentheses 1 plus y, equals minus 2 cosine of x plus the arbitrary constant. Okay. So that would be the general solution of the differential equation, but we want to go through 0, 0, and that allows us to get the value c1. So let's plug in x equal to 0, y equal to 0, and see what c1 comes out to be. When you plug in y equals to 0, the exponential 0 is 1, plus, what happens here? 1, right? Equals what? Minus 2, cosine of 0 is 1, plus c sub 1. Therefore, c sub 1 is equal to 4. Okay? And the solution to the differential equation, therefore, let me go back over here. I'm just going to plug in the value of the c. So the solution, finally, to this problem, and remember, dy is what we started with. Okay, here's the curve that solves this. E to the y plus e to the negative y, parentheses y plus 1, plus 2 cosine of x is equal to 4. Right? That's the solution. Okay, now I want to show you, again, what you should be developing, is a good, like a synergy between analytical solutions, and, using the computer. Okay, there's no way to solve that in y terms of x. So what's interesting is that we had the differential equation was separable, one of the easiest types, okay? We're able to get the constant of integration, okay? We have the solution, but we can't get y in terms of x, okay? But I want to at least get a graph of y versus x, okay? So let's see how we can go about doing that. First, I'm going to show you, I wrote a routine that I think I illustrated it once. If you go to the Moodle page, there's, besides direction field, there's another one called contour.m. And that allows you, remember, to take an f of x, y equals constant, no matter how complicated it is, and graph it. Okay? You can modify it for this, you should modify it for this problem, and you'll see the graph that I'll show you in a second here. Let me just get it up on the computer. Let me tell you this guy. And actually, I'm going to do a little more than the book has on it. There's a lot of stuff that the book didn't mention about this that you can tell by just looking at it, and I think you'll find it interesting. They just kind of leave it short, which is unfortunate. Separable. First thing to show you is the direction field. Okay? And then we'll actually look at the solution. Kind of blew it up a little, maybe I can just decrease the magnification a bit. Okay, so there's the direction field, right? That's what we started with. dy dx is e to y sine 2x divided by cos x, e to y minus y. And you can see what the direction field looks like, right? Okay, remember there, but I just basically went over the whole xy plane and I didn't assume any value for the constant, right? I just got the direction field. Now, if you recall, we solved this subject to the initial condition that it goes through 0, 0. Let's try to see what that looks like. Here's 0, there's 0, right? It looks almost like a parabola, right? If you follow it, kind of going through 0, 0. Okay? And then what I did is I used that function in MATLAB that I gave you called contour.m, and I said plot, you know, exactly what I had on the board. And then let's see what that looks like. Okay. And basically that's, remember I said there was a parabola? And I think I probably just didn't go out far enough, okay? And actually if you take that solution and use contourplot.m, you'll find out that you get this kind of curve over here. And the question is, what happens, the book I think just does it like to here or something like that. You get this and it stops. What's interesting about this is this keep going on like this and repeat itself, okay? And let me show you, there it is, okay. Just look at the equation, okay? Suppose you have a point xy that's on the graph, like over here, okay? You'll notice basically that it's periodic as a cosine x, right? So if I have a certain xy that's on the graph where my finger is over here, if I increase x by 2 pi, the cosine goes back, it's the same, right? So therefore, this thing is actually periodic of period 2 pi, and that's exactly what you see over here. I don't have the numbers on the x-axis over here, but actually this is around, if you look at it, it'll be about 6.2, something like that, 6.28, okay? So what happens is that the solution actually repeats. Not only that, you can actually show that it's symmetric with respect to this, where the maximum is, okay? If you draw a line over there, it's symmetric. So actually, if you just have the solution from here to here, you've got it for all values of x. You flip it over here to make it symmetric, then you've got it over here, okay? It's an even function because of the cosine. Then you have it over a full period, and you just keep repeating this. So the solution to this differential equation is very interesting in the fact that it's this periodic pattern that you see over here, okay? One period, you know, can go from here to here. There it is. Okay, then it just repeats again. Okay? And what's interesting is that you may not have thought of that if you look at the graph, but then it's obvious when you look at the graph, oh yeah, I've got cosine x in there. So if I got a point on the graph and I just shift my x by 2 pi, I'm going to get the same point again. That's exactly what that graph shows. Okay. Else here, I'm going to before I turn off the machine. Okay, I'll just do one more, I think, and that's it for this topic. Okay, solutions in terms of integrals. Okay, What will happen many times is that you'll get a solution to a differential equation and you can't do the integrations, okay? Happens a lot, like in probability, you get these EDX squares, or in thermodynamics, when you do statistical mechanics, look at the equilibrium phases of a gas, you get all these crazy functions that you really just can't integrate and actually tabulate it, okay? Remember I told you MATLAB has all these special functions around, okay? And the reason is because in applications, they come time and time again, and of course now with things like, you know, before they used to have tables. If you go to the library, probably still have it. You can look at this table. It's called, this was interesting. It was one of the most, I forget how many copies this thing sold. It was one of the most popular references used by engineers and physicists, you know, for many, many years. It was from the National Bureau of Standards, which now it's no longer called NBS. It's now called the Institute for Standards Technology. Okay, and they had a project after World War II. It's called the Handbook of Mathematical Functions. Every library has it someplace. You'll probably pull it out with the old dusty now. Just table after table and graphs of all these special functions. Of course, today we have all these things built into computer programs like Mathematica and MATLAB, so you don't need those anymore. But the fact is they come up a lot in different applications. Okay, so let's look at this. And we're not going to deal with these type of equations really, because the idea here is being able to solve differential equations. But I just want to give you a flavor for what can happen. dy dx is e to the minus x squared. That's your famous Gaussian. Okay. And suppose I want this thing to go through the point. What is it? 3, 5. y3 is equal to 5. Okay. That one's even easier than variable separable, right? Because you know it's dy dx is just a function of x. So you bring this stuff to the other side, right? You get dy is e to the minus x squared dx, okay? And then you integrate both sides, right? So what happens over here, you get y equals the integral of e to the minus x squared dx, indefinite integral. You can't do that integral in terms of closed function, you can't do it in closed form, okay? It's basically called the probability integral. This occurs a lot with normal distributions. Like I said, it occurs a lot in thermodynamics, okay? And it's been tabulated, okay? Some people call it the error function, okay? And what you'll find tabulated is not the indefinite integral, of course, because there's no expression for it, but the definite integral between different points. It really represents the area under this normal distribution. So if you graph e to the minus x squared, basically it looks like this, right over here. And there'll be tables that'll tell you what the area is at a certain x. X equals 5, x equals 8, okay? In statistics, they have these things all over the place. Okay, so what I'm going to do now is kind of make it into like a definite integral, okay? Because that's the thing that will be tabulated, those things that you can look up. And the trick in doing that is the following. What I'm going to do is see the problem is when I do the integral, leave it like that, it's ambiguous. It says, what's the arbitrary constant? Okay? And unfortunately, I can't do the antiderivatives, I can't write it down. So what you want to do basically is write this in the following way. Let's do this to the integral, say, from 0 to x of e to the minus x squared dx plus an arbitrary constant. Okay? I haven't solved it at all. I've just expressed it in terms of a definite integral, but it's between 0 and x, where x could be anything. And then another thing is, so you don't get confused, I'm going to change the dummy variable of integration. You recall from calculus, for example, that the integral from 0 to 1, let's say, of x squared dx is the same as the integral from 0 to 1 of t squared dt. It's a dummy variable of integration, right? It just integrates out. So what I'm going to do here is make it e to the minus t squared dt, so I don't have a confusion between the dummy variable of integration and the limit, 0 to x, okay, plus an arbitrary constant. Okay. So that's the solution to the differential equation, but it's an integral form because you can't do that integral e to the minus t squared with respect to t. Okay? But let's get the initial condition there, get rid of that c1. We know that y3 is equal to 5. So what's y at x equal to 3? Now you can see why I went from here to here, so that the x is here, not over here. You get confused if I said x equals 3, you may put it here by mistake. You have to realize here it's just an integration variable. So a lot of times what's good, you just change it so you don't make that mistake. Make it e to the minus t squared so you don't confuse the dummy variable with the limit. Okay, let's plug in x equal to 3. y of 3. So now it's the integral from 0 to 3 of e to the minus t squared dt, right, plus c sub 1, right? But we know y of 3 is supposed to be 5. So it allows us to express the constant c1 as 5 minus, even though I don't know this is a definite number. The integral from 0 to 3 e minus t squared dt, you can look that up. It'll give you a numerical value, or you can look up in a table. Okay? It'll be the area under that curve between 0 and 3, a definite number. So let's just leave it like that. Okay? And now let's go back to our y of x and finish this up. Okay? So what's y as a function of x? I'm going to go back to this one over here, plug in the value of c1. So it's the integral from t equals 0 to t equals x of e to the minus t squared dt, right? Plus c sub 1. I just found that. 5 minus the integral of 0 to 3 of e to the minus t squared dt. Okay, so I plug in. We can even do better than that. Okay, remember from calculus, if I integrate e to the minus t squared between 0 and x, think of it as the area under the curve. I subtract the area of the curve from 0 to 3, I'm left with what? The integral from, just give you, right, I've got this curve over here, right? Integral from 0 to x, the area under there, 0 to 3 would be this thing over here. So I could write y of x, finally, as 5, right? Integral from 0 to x, that area, minus the integral from 0 to 3. Oh, that's just the integral from 3 to x of e to the minus t squared dt. So you can see that when y equals 3, right? Sorry, when x equals 3, y is equal to 5. If I plug the x equal to 3, I got the integral from 3 to 3, which is 0. Yeah, y of 3 is 5. And that way, this is something you could program up, and use MATLAB to actually get y as a function of x and then plot it. Okay? So this does happen. Like I said, we're not going to do too much of this, but what's important, like I said, when you take more advanced courses in engineering, a lot of times you'll get things like this. There are functions defined by integrals. Another one is called a gamma function. That occurs a lot also in probability and also in statistical mechanics. Again, dealing with ideal gases, okay? And all these things are tabulated, okay? So I think this is probably a good point to stop. Like I said, I'm going to put up a homework. It'll be very